next talk is on separations and communication complexity by Anshu, then David, Bellows, Goose, Jane, Kothari, Lee, Santa, and Robin Kothari will give the talk.
Thanks for the introduction. You guys can all hear me? Okay, I think you can hear me. All right, so thanks for coming to my talk. This talk is going to be about separations in communication complexity using cheat sheets and information complexity. And this is joint work with a couple of people, so let me introduce the cast. Anurag Anshu is a grad student in Singapore. Shalaf Ben David is a grad student at MIT. He's also here, and he's on the job market this year. Alexander Bellows, faculty at the University of Latvia. Mika Goose is a postdoc at Harvard. He's also here and giving the next talk. Rahul Jain is also here, faculty at Singapore. I'm Robin Kothari. I'm a postdoc at MIT. I'm also on the job market this year. Troy Lee, faculty at Singapore, and Miklos Santos, faculty at Paris and Singapore. All right, now that we got that out of the way, you're probably thinking, how did this collaboration happen with this number of people? And the answer is really simple. We were all at a conference in Singapore, and one day this happened. Someone's like, guys, I got this. Cheat sheets in communication complexity. And we were all sold on the idea, and this is what happened. Okay, so in more seriousness, what this talk is about is proving new total function separations in communication complexity using a framework from query complexity that's called the cheat sheet framework, the thing I referred to on the previous slide. Okay, so this is the communication complexity session, so I kind of don't even almost have to introduce this model, but this slide has to be there, so it's here. Communication complexity. Okay, so it's the usual thing. There's some input. X goes to Alice, Y goes to Bob. They're trying to compute some joint function, f of x comma y. They talk to each other. They want to minimize the amount of bits communicated. Depending on the kind of resources that they're allowed, you can define different models. Deterministic communication complexity, which I'll denote by D of f, is exactly what you think it is. Randomized communication complexity is similar to deterministic, except now they have private and public randomness, and they're allowed to get the answer wrong with some small probability. And Q of f will denote quantum communication complexity, which I won't define, and you don't need to know for the rest of the talk. It's just, I literally want you to know only one thing about quantum communication complexity, that it's a model of communication complexity that's better than randomized communication complexity. So that's all you need to know. Okay. There was no quantum in the title, so I hope you guys are not like, oh my gosh, this is a quantum talk, I should. Because you really don't need to know anything other than this inequality over here. The Q of f is less than or equal to R of f. All right. So now that I've introduced quantum communication complexity and randomized communication complexity, we can ask the separation question, which is, can quantum communication complexity be smaller than randomized communication complexity? And this is actually a favorite question of us quantum computing types. We love asking this question in every model of computation. Can quantum do better than randomized? And in communication complexity, if you consider partial functions, which is something I did not define on the last slide, but partial functions are functions from some restricted subset of the input space x times y to 0, 1. So you have some promise on the input that only certain pairs are allowed. If you restrict to partial functions, then exponential separations are possible. So this is great, and we're not really going to talk about partial functions for the rest of the talk. The focus of this talk is total functions, which are the kinds of functions I talked about on the previous slide. And for total functions, essentially, prior to our work, the best known separation was quadratic, and it was because of disjointness problem, whose randomized communication complexity is n, famously, and its quantum communication complexity is root n, which is essentially due to Grover's algorithm, although to get rid of all the log factors, you need some work from Aronson and Ambinus, but essentially you get this quadratic separation from Grover's algorithm. And so you might ask, is it possible to beat this Grover separation? Is it possible to get a super Grover separation? And this joke gets like a ton of laughs at quantum computing conferences, just so you know. Everyone loves Grover over there. But this is our main result, basically. We say, yes, it's possible to get this super Grover separation, which means we can get a separation between randomized and quantum communication complexity that's more than quadratic, and it's a power 2.5 separation. All right, so this is our first main result. There's going to be two main results in this talk. And here's some fun facts about this result. Well, there's only one fun fact, which is that it actually also works with information complexity, which is a thing we heard about in the first talk. So what I mean by that is you can replace randomized communication complexity here with information complexity, which is a lower bound on randomized communication complexity, so that's a stronger result. But I won't define what information complexity is, and I'm not going to use it for the rest of the talk. But for those of you who know, we also get this separation. And we also get a bonus result from our techniques, which is that there's a separation between bounded error randomized, like the model we're working with, and exact quantum algorithms. Okay, I'm not going to define what exact quantum algorithms are. Also, probably nobody cares. But we just want you to know that there's something you get basically from our technique. It just pops out for free. So it's a bonus result. OK, so that's the first main result. Let me tell you about our second main result. And the second main result is to do with this quantity called the partition number, which I'm going to denote by Pn of f. And I'm not really going to define what the partition number of f is, because it's either you work in communication complexity and you know exactly what it is, or you have no idea what it is, and it'll take me 2 minutes to define it. So it's not very relevant. And the reason I'm talking about it is because how it relates to all the other communication complexity measures. And the relationship I want to highlight is that this partition number is an upper bound on almost every lower bound technique that you know. So every lower bound technique for either deterministic communication complexity or randomized communication complexity, like the log rank, non-negative rank, approximate rank, the corruption bound, discrepancy, the partition bounds, basically every lower bound technique you know, with the notable exception of information complexity, is upper bounded by this guy, the partition number. And OK, for the experts in the audience, I'll just tell you what partition number is. It's the logarithm of the minimum number of monochromatic rectangles any partition of the communication matrix. OK, so if you're working communication complexity, you know what this is. Otherwise, don't worry about it. The relationship I want to focus on is that it's an upper bound on every lower bound technique. So why should we care about upper bounds on every lower bound technique? Because then we can ask the separation question, which is, again, can this partition number be smaller than deterministic communication complexity or randomized communication complexity? And if it can be, this is going to be a problem, because this means all of our lower bounds are going to fail to prove good lower bounds, because partition number is an upper bound on all of the lower bound techniques. And if we separate it from the measures that we're trying to lower bound, that means there's always going to be a gap. And you're not going to have good lower bounds for some functions, at least for those functions for which we prove the separation. And this question turns out to be really hard, exactly for the reason that the partition number lower bounds all lower bound techniques. So how would you prove a separation between either deterministic or randomized communication complexity and partition number if you don't have techniques to prove the separation? And because of this reason, until last year, the best known separation was just a factor 2 separation, like a multiplicative factor 2 separation. And this stood since 1997. And last year, there was a breakthrough by Goose, Pitassi, and Watson, and they showed a power 1.5 separation between deterministic communication complexity and the partition number. So this is the first superlinear separation between these two measures. And then later on, they followed it up with Jairam. They improved this separation to, they had the same right-hand side, but now it's gone from deterministic to randomized. So it's a lower bound against a stronger model. And then finally, again, last year in December, Ambayanis, Kokainis, and myself, we improved the original separation from 1.5 to essentially 2 minus little o of 1. And if you look at this sequence of results, you see there's one result that's conspicuously missing, which is now we need to extend this guy to get randomized communication complexity on the left-hand side, and that's what we prove in this work, that indeed we can do this. And these results stop at quadratic because actually there's a general result that says for any total function f, both the randomized and deterministic communication complexities are upper bounded by the square of the partition number. So quadratic is the best you can get, and we essentially have quadratic. So this essentially settles this problem. OK, so these are the two main results, the separation between quantum and randomized communication complexity, and the separation between randomized communication complexity and partition number. So in the remaining time, I'm going to try to explain the techniques that go into this work. All right. So before I start talking about the techniques, I should mention that for all of these results, the analogous results in query complexity, or decision tree complexity, are already known. So I mean, analogous to communication complexity and query complexity, you can define all of these measures. You can define deterministic query complexity, randomized query complexity, quantum query complexity, the partition number, and so on. And we know the analogous separations in query complexity. So this suggests an obvious proof technique, which is you use a lifting theorem and lift the separation from query complexity. And so what that would mean is, first you start off with a function that already exhibits the separation in query complexity. So for example, there is a function which has this 2.5 power separation between randomized and quantum query complexities. And this is due to Aronson, Ben David, and myself, and this was presented at STOCK this summer. And this construction uses this cheat sheet framework that I was talking about. And so you start with this function, and just for a notation, I'm going to use the superscript dt to denote decision tree. So whenever complexity measure has DT on it, it's a query complexity measure, not a communication complexity measure. The communication measures don't have any superscripts because this is the communication complexity session, so that's more fundamental. So what would you do with this separation? What you do with this query function, so this is a function on n bits, right? And now you want a function in the world of communication complexity. So you lift this function. And lifting theorems have appeared in almost every session of this conference, it seems. Everywhere I go, I see lifting theorems. So I know a lot of you are familiar with it, but just let me recap what a lifting theorem does again. What it does is it takes a function in query complexity, so a function with n-bit input, 1-bit output, and converts it to a communication complexity function. And how does it do that? It takes your query function, and it attaches these little communication gadgets to its input. So this is a communication complexity problem, which means it has two kinds of inputs, the Alice input and the Bob input. And what you do for this composed function is you give all the Alice inputs to Alice, give all the Bob inputs to Bob, and the output of the function is Alice and Bob compute this function g. They get 1-bit output here, they get 1-bit output here, 1-bit output here. This is 3 bits in this example, and then they compute f on this 3-bit function. So that defines a communication problem from a query problem and from this function g, which we sometimes call the gadget. So you should think of the gadget as being very small, either a constant sized object or a log n sized object. So we're not going to think about the complexity of the gadget. The gadget is essentially easy or cheap, or its complexity will be hidden under the tilde notation. So we don't really need to worry about this. All right, so what you can say about this lifted function is that this upper bound direction, that the communication complexity of the lifted function is upper bounded by the query complexity of the function you started with. This is usually true in like almost every model of computation that you would care about: deterministic, randomized, non-deterministic, quantum, whatever you think about. This is always true, and the reason for that is Alice and Bob can just mimic the query protocol. Like whatever was the first variable that was going to be queried, let's say this guy was going to be queried, Alice and Bob can compute this gadget. The gadget is cheap to compute, and now they both know the answer to this variable. Then they can do the next step of the query protocol and so on. So Alice and Bob can always just mimic the query protocol. So there's nothing interesting going on. The upper bound always works. And what is highly non-trivial is that sometimes you can prove matching lower bounds, and these are often called lifting theorems. So for deterministic communication complexity, you can actually prove this lower bound, which says that basically the best strategy for computing this function is for Alice and Bob to mimic the query protocol, and there's no better strategy. So this was proved last year by Gibbs, Patasi, and Watson, building upon the techniques of Raz and McKenzie for deterministic communication. So why am I talking about these lifting theorems? I'm talking about them because if we had a lifting theorem for randomized communication complexity, then we would be done. And how does that work? A lifting theorem for randomized communication complexity would prove our result using these 3 inequalities. The first one is just the statement of the lifting theorem, that the communication problem's complexity is lower bounded by the problem of the query complexity of the problem. This guy is a power 2.5 bigger than the query complexity, the quantum query complexity of the problem. This is the query result that we know to be true. And this guy is lower bounded by the quantum communication complexity problem. This you get by using this upper bound works in most models fact, because I mean there's omegas over here, but if you flip it around, it's just an upper bound statement. It just says that the quantum communication complexity players can just mimic the quantum query protocol. So this is a completely trivial statement. This is the assumed lifting theorem, and this is the known separation and query complexity. So if we had a lifting theorem for randomized communication complexity, actually all the results in this paper are trivial. So there's nothing to do. So obviously the reason why this paper exists is that there's no lifting theorem known for randomized communication complexity, and this is a major open problem. And I encourage you to work on it if you're into that kind of thing. Okay, so now that we don't have this, what should we do, right? So what we can try to do is we can try to mimic the query separation. So we're not able to lift the query result. We're not just able to apply some black box hammer and say, done. Query separation implies communication complexity separation. But we can follow the same proof idea. And how do you mimic the query separation? So let me give you a rough idea of how the query separation goes and how you would go about mimicking it. And throughout the separation, we're just going to focus on proving the randomized lower bound. So it's a separation. So actually it has 2 components, a lower bound and an upper bound, because that's how you separate 2 things. But the upper bound is quantum, so I'd have to talk about quantum things. But secondly, the upper bound always just works out. So just don't worry about it. The upper bound will just work fine. So we just have to focus on the randomized lower bound. So how does the separation work in query complexity? So the query separation starts out with some very special function f, which I won't describe to you. But this function has the requisite separation property. Its complexity is 2.5 times bigger for randomized than quantum. But the problem is it's a partial function. It's not a total function. And then what you do is you apply this cheat sheet framework that I talked about from this previous work, which converts the original Boolean function into a new Boolean function, which I'm going to call f sub cs for cheat sheet. And this function is going to be total and going to still have the same properties. So its randomized communication complexity is going to be lower bounded by this guy's randomized communication complexity. And that's going to give us our separation. OK, that's great. And this was proved, as I said, in this work from earlier this year, or last year, I guess, and which shows that the query complexity of this cheat sheet function is lower bounded by the query complexity of your starting function. All right, that's great. The strategy that I proposed on the previous slide, the one that doesn't work, just lifting, would involve going from here to here. You say you compose with some gadget. And the problem is we don't have a lifting theorem. So we don't have a way of saying that the randomized communication complexity of the lifted problem is lower bounded by the randomized query complexity of the original problem. This is not a statement that we know how to prove in general. This is open. All right, so this is the approach that doesn't work. So then we thought about this for a bit, and we thought, all right, we don't know how to lift randomized query complexity. Maybe we can lift a lower bound technique for randomized query complexity. A lower bound technique that doesn't also lower bound quantum communication complexity, because then you wouldn't be able to have the separation. And in fact, there is a lower bound technique for randomized communication complexity that does not lower bound quantum communication complexity, and a lifting theorem is known for this. And this is something that in query complexity is called the conical Hunter degree, and in communication complexity it's sometimes called the smooth rectangle bound or the approximate non-negative rank. And for this quantity, we do have a lifting theorem, so that's great. We can lift it, but the problem is you would also have to start out with this function f and show that the conical Hunter degree of this cheat sheet function is also high. And this is something we don't know how to do. So we don't know how to say that if the original function you started out with had high conical Hunter degree, whatever that is, I'm not going to define it, then once you apply this cheat sheet transformation, the conical Hunter degree remains high. So OK, we don't know how to prove that, so that's a shame. So what do we do? So we do the only thing we can do, which is from here, we have a lower bound in its conical Hunter degree, and we have a lifting theorem for conical Hunter degree. So we first lift it. So this is fine. You can lift it because this is a thing we have a lower bound for. We use this known lifting theorem. What do you do from here? Like, you've already lifted it. There's only one thing to do, which is to apply this cheat sheet transformation. So we apply it. But this kind of doesn't type check, because this cheat sheet transformation was only defined for query functions, like for Boolean functions that take an n bits input and 1 bit output. So we have to define what it means to apply the cheat sheet transformation in the world of communication complexity. So that's something that we do in this work. But we don't claim this is a great innovative part of this work, because you basically take the cheat sheet transformation in query complexity and do the most natural thing in communication complexity, and you'll get our definition. So that's not really innovative. The really hard part is to prove this technical result, which says that the communication complexity of the cheat sheet problem is lower bounded by the communication complexity of the problem you started off with. So this is the analogous result of this result over here, which worked in query complexity. We need to prove this in communication complexity. So in other words, the main technical result is just that the randomized communication complexity of the cheat sheet version of a function is lower bounded by the randomized communication complexity of the original function. This is the main technical result, which obviously I'm not going to prove. I encourage you to read the proof in the paper. It starts out with this very friendly flowchart telling you how to read the proof. So, I mean, the proof can't be too bad, right? If there's a friendly flowchart to guide you through the proof. So, OK, that's all I'm going to say about the proof. And about the cheat sheet transformation, as I said, it's a transformation that looks very similar to the query world, where you start out with some function in the communication world, f, and now you want to convert it to a new function in the communication world. And you just do this very simple transformation where you take many copies of it and add a cheat sheet. All right, now, so this is kind of complicated, and it's also something I don't want to get into. Again, as I said, it's not something we claim to be the innovative part of our work. It's almost exactly the same thing as in the query world, but you just have to think about it and do it in the communication world, and it works out. So this is fine. I just want to spend a minute talking about the second result that I talked about, which was the separation between randomized communication and partition number, because this doesn't work straightforwardly. And the issue is that the function that's used in the query complexity world has this kind of structure, where you start off with some base function g, apply the cheat sheet construction, compose it with g, apply the cheat sheet construction, compose it with g, and do this some number of times. And so you just need to prove two things about this function to get the separation to work. The first thing is that when you apply the cheat sheet construction, the query complexity does not go down. And we just proved a communication complexity version of this. So that's fine. The second fact that's used in query complexity is that when you compose with the AND function on n bits, the complexity goes up by a factor of n. This is true in query complexity, but it's false in communication complexity. So this proof sketch cannot go through, because this statement is just simply false. It's not open, it's just false. And there are many simple examples, but you can just try to construct a function, communication function, where taking the AND of many copies of it is still has the same complexity as the original problem. And there's a fix. And the way we fix this is to do everything all over again, but now do it with information complexity instead of randomized communication complexity, because with information complexity, you can prove a statement something like this. And then this communication analog that I said we just proved with the very nice and friendly flowchart, you just go and do all of that all over again, but now do it with information complexity. So that works out, and you can see in our paper that we prove both statements together, the information complexity statement and the randomized communication complexity statement. And we prove this thing, and basically we mimic the exact query strategy. Everything works out as you expect it to. All right. And so that's basically an overview of how we prove the two results I claimed. And let me end with some open problems. I think the main open problem is to prove a lifting theorem for randomized communication complexity, because as I said, this would imply all the results in this paper. Another fun fact is, if you proved a lifting theorem for zero-error randomized communication complexity, this is actually no easier because it implies a lifting theorem for randomized communication complexity. So there's some lifting open problems, and there's also general open problems about what we can say about the separation between quantum and randomized communication complexities. We don't know whether they're polynomially related or not for total functions, which is something we know in query complexity, but we don't know in communication complexity. So it's possible that our 2.5 separation is completely going to be dwarfed by some exponential separation in the future. So that's something that's also open. It's also open in one-way communication complexity to show even a super linear separation between quantum and randomized. Basically, no separation is known. All right. And that's all I wanted to say. Thanks for your attention.
Questions?
Sorry, might the result be speeding up what to the to the classical prover? Oh, the Grover algorithm. No, the Grover algorithm is tight. So for the problem that it solves, the quadratic is indeed the best you can do, and that's something you can prove. So I guess the moral of the story is just that that problem is not the right problem to look at. You have to look at a different problem. There is a similar problem that works in query complexity as well, which also has the 2.5 separation and is a total function. It's just not the same problem that's being solved by Grover's algorithm. You need a different algorithm to solve it.
Let's thank Robin again.